نعم. طب حضرتك تبدأ الديسيشن بتاعتك مع الطلبة النهارده ولا؟
ثلاثة سوا
خلاص.
هو يوم الثلاث.
دلوقتي المحاضرة والتوتوريال بتاع دكتور محمود هيتأجلوا ليوم الثلاث. اوكي. فالناس اللي هي كانت بتروح مع دكتور محمود البروجكت you are free to join. You can join. Oh, تقدر Okay, so today that's lecture number 3, and we are going to discuss a bit about the concept of. And we are going to discuss a bit about the concept of ensemble learning. As an example of the ensemble learning is the decision trees, random forest and boosted decision trees. From the name, like ensemble learning, you can get some intuition about what is the ensemble learning is actually. So it's kind of, you have different machine learning models, and one tries actually to combine those models to have a good or a model at the end that can achieve a high accuracy or high performance, like the way that you combine different machine learning models at the end. And the point now is what is the mechanism that we use actually to combine those models, right? So how we combine those. So for example, if you like sequentially combine the model using some boost algorithm, this is what's called boosted decision trees. And if you combine different decision trees like randomly and you aggregate at the end, this is what's called a random forest. So this is the topic of today. Is first we need to understand what is a decision tree or a regression tree, and then we want to discuss a bit on how a different way of ensembling different many of the decision tree to have ensemble learning like the boosted decision tree or random forest. Well, so nope. Sure. Okay, so this is the normal tree, right? So this is the tree that we know, and this is the tree that gives us all the needed food. And this is the nozzle tree, and actually this is the tree that we are talking about. So the main difference here between the normal tree and the decision tree, that the decision tree that we want to construct and we want to study, it gives us extra information, which is the decision. So, like, as you can see, like, we call this a decision tree because it's a tree, right? So it has a nodes, it has some branches, it has leaves, it has everything. But additionally, it can give us a decision. It can give us, help us to make a decision by giving us some probability or information that this decision tree can give us. So what is exactly the advantage of the decision tree over other machine learning models? So now consider that we have a nonlinear separable data, like two classes of data, the red points and the blue points, right? And those data are nonlinear separable. So to separate or to find a classification boundary that separate between the two classes, we need to form a classification boundary like a circle or some ellipse things like that. So we've discussed, like in the last lecture, about the linear model, right? So we discussed the linear model, like the linear regression model, like gradient, lasso, and all of these kind of things. And as you can see, if we use a linear model trying to classify the points from the two different classes, then those linear models actually can predict only a linear classifier, right? Right? Because it can predict only a linear classifier, which is nothing but the line. And as you can see, this is ridge CV, this is vanilla ridge, this is linear regression, this is Bayesian ridge, and that one is stochastic gradient descent method, and all of them are linear model. So the problem is that now, if for example, all of these classification models, once they actually find the classification boundary like a model, can I ask you what is exactly the accuracy in this case, for example? Can one predict what is the accuracy in this case? 50%? Exactly. Right? So the model actually can predict the accuracy, the blue points or the red points, with only 50%, because half of the red points are above the classification boundary, and the second half is down to the classification boundary, right? So we need a source of more complicated machine learning models, like for example, the boosted decision tree or a deep neural network. And in today's lecture, we are going to discuss about the boosted decision trees, and random forest. And in the next lecture, which is tomorrow, we are going to have a very, very deep, detailed discussion about the deep neural network. So as you can see here, for the boosted decision tree, now the model actually is able to classify the points from two classes correctly. So here we have, this is the classification boundary. Here, if the points lies over here, then it most likely be or classified as a red point. And if it lies inside here, then it classified as most likely being a blue point. So this is one of the advantages of why we need a more complicated or complex machine learning model than the simple linear regression model. Well, so how actually this decision tree works, right? So the mechanism of the decision tree, we all have done it when we were kids, right? So a friend of you actually might ask you, like, can you predict or give you some riddle, riddle, right? And then it asks you, can you predict the name of the animal? And then you start asking back, trying to get some answer. But your questions to your friend is not like a direct questions. It's just like a generic questions, try to get some intuition or information about what this animal is, like the nature of this animal or the features of this animal. So it just asks you, okay, can you please guess some animal or something in mind? And then you ask him, okay, so does this animal have some feathers? And then he gave you answer. So if he said true, then you have more information, right? So as far as you ask him the questions and he give you back some answer, then you get more and more information about the characteristic features of this animal. So if he answer you that yes, this animal has the feather, then you ask him the second question. Okay, so this animal can fly. So if he say yes, then you may get in your mind this is properties of how. If not, then it may be that animal is a penguin. And on the other hand, if you ask him from the beginning that does this animal have some feather, and then he said no, then you ask another question is, does this animal have some fins? So if the answer is yes, then it might be most probably be a dolphin or any other kind of fish. If not, then it might be another animal like deer or something like that. So this is how things work. You start with a big question, and now you start asking different questions such that from the answer of these questions, you can get information about the nature or the characteristic features of the data that you try to analyze. Well, so how that works in detail. So, of course, the decision tree, we have also the regression tree, right? So, anybody answer the difference? Know the difference? Yes? No? Okay. So, you know what's the difference between decision and regression? Yeah? We mentioned that in yesterday's lecture. The difference between classification and regression, right? Right?
Yes.
Yes. So what's the classification is?
Classification. We have two labels.
You have your data that you try to analyze can be categorized.
Categorized, yes.
Right?
And be labeled.
Yes.
The other type of, for regression we have
Continuous.
values. Yes.
Right? So yes. So please keep that in mind because this is very important. So we have the decision, which I'm going to discuss here, but only very similar to it, we have the regression tree, and the difference between them is the type of data that we try to analyze. Okay. So how it works? So we start with the root node. We just pick some data, random data from the inputs, and this is considered as root node. And then you ask questions or try to find the best classification boundary between the two data, because you have both classes together, right? Like you have the blue and red points together in one set, in one node, right? So they are distributed. They have the X and Y, right? So we try to find the best separation that, or the best classification boundary that can separate between the data from the two classes on that node, right? And then once the algorithm that you've created, which is the decision tree, find the optimal threshold, then that gives the best separation between signal and background by calculating the loss function. Then once this threshold has been found, then the node splits. You split it into two nodes, right? So we have inside here, we have a set of points, blue and red points. Once we found the best classification boundary, then we split. This branch takes the blue points, or most likely blue points, and this branch takes the most likely red points. And then for the branches, those branches here, which are not mostly signal or like from the first class or the second class, we call them as impure branches, right? So as you can see here, it has a set of red points and also a set of blue points. Same here. So those are impure. They are not pure. So as far as those branches are not pure branches, it means that it contains points from two classes together in one branch. Then we consider them as the first node here and split them again. And we keep splitting until we hit a leaf. And this leaf contains the most likely all the points from the first class, or the other leaf here contains points from the second class. So at the end, we have a tree that all the nodes or the leaves of this tree contains pure points from different classes. Okay. Well, so now the question two questions actually we need to ask ourselves. The first one, when do we have to split the node, right? So what is exactly the criteria that we can follow to split the node, the impure? And second question is, when do we have to stop splitting, right? So when we have to split, and also when do we have to stop the split? Well, so before I go into the criteria to split the impure nodes, I would like to introduce what's called the purity. So the purity is, you can define the purity as events from the first class over events from the first class plus the events from the second class. So for example, here those are two impure nodes, right? So they have points like red points, and they have also a yellow points, right? So they contain points from different classes. So those are impure nodes. That one here and that one here. So if you look at the purity, then this purity actually ranges from 0 to 1, right? How that happens? Like here, if I have this S, if I have the B equal 0, that means there is no any yellow points over here, right? As you can see here, then the purity is 1, right? This B is 0, no yellow points. On this, the other set or the other node, where we have no S points, no red points, then the purity is 0, right? So we have 0 over B, which is 0. So those are leaves, those are pure nodes. For the impure nodes that we split this node, but the split was not perfect. That means we still, even for the splitted branches or the splitted nodes, we still have some red points together with the yellow points. So this is still the separation or the splitting of the root node was not perfect. So we still have the purity is not ranging between 0 and 1. So now the questions here, or you can get an intuition that we actually tends to find what is exactly the separation or the separation method that we can use such that the points are classified or lined into two pure nodes, which we call them as the leaves. So how can we do that? Of course, we have the criteria, right? We need to minimize the error function, right? Always, right? So what kind of loss function we can use here? So as you can see, we introduced the purity, right? So all the used loss functions should contain the concept of the purity. So actually the default one is what's called Gini index. And that Gini index, it has the form of B dot 1 minus P, where P is the purity that I was just mentioning. Well, so how this loss function looks like. So here this is the Gini index versus the purity. So the Gini index actually maximize at the purity is 0.5. So at 0.5 purity, the Gini index is maximum, right? This is logic, right? So what does that mean? The purity is half. Answer? Exactly. So this is the highest misclassification. I have everything in one set. And that should gives you the large error, right? So we need to minimize this Gini index. But the point is that if we minimize this Gini index, it has two values for the purity. So the minimization here, I mean the minimization of Gini index, it can have a purity of 0 or purity of 1, right? Look that here. So if P is 0, the Gini index is 0, right? Also, if P is 1, the Gini index is 0. So that's the good thing. Because to classify the data that you have to be either in the first class or from the second class, that we need two things together to control this operation. The first one is that we need to minimize the Gini index. The second one is we need to measure the purity. So if the purity is large than 0.5 and the Gini index is minimum, then we hit a leaf or a pure node from the first class. On the other hand, if the Gini index is minimum, but the purity is less than 0.5, then we have a pure node or a pure leaf from the second class. Got it? This is exactly the case here. So on those two nodes, the error function and the Gini index is minimum, right? But the only difference is that the purity here is 0 and here the purity is 1. Just to give us an indication, what are the points inside the nodes. Like either these points belongs to the yellow class or the red class. Well, so now we answer the first question, which is what is exactly the criteria that gives us the best splitting of the impure node. And now the second question is what is the criteria to stop splitting, right? So we can keep split the impure nodes. In principle, we can do that. So as far as you found impure nodes, like nodes have the points from different classes, you keep split, keep split, keep split, keep split until you have leaves at the end that contains the events from or points from the first class or points from the second class. But this is not true. This is not the true answer, because if you remember the overfitting problem, right? So we have this digit. We cannot do that. Right? So the overfitting here, this is also an explanation. So during this whole lectures, every lecture I'm going to talk about overfitting, 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 because this is actually a killing problem in machine learning when you deal with the machine learning. So this is how the overfitting looks like. It means that if you create, like if you classify all your points and into complete leaves, where each leaf contains only points from the first class or second class, then the model also classify the noise. So if you have a noise in your data, if your data has some noise, then you classify this noise as well, as if it belongs to the first class or the second class. And this is what makes the problem of the overfitting. So we should not do the overfitting. I gave you an example, and that makes everything very clear. Well, so we have a set of red and blue points, okay? And we want to classify them. So we start with a sample of points together, 200. 100 of points from the first class, like 100 red and 100 blue points. Those here together, right? And I start like random guessing. All points are classified as red points. So this is my start guessing, like my initial guessing. So how do we separate this at the beginning? Okay, we said okay, this we have a y feature and x feature, right? So we said okay, if you take y less than or equal 0.381, that means we could have some splitting, right? So you just use the y here to split. So after this is split, what's going on? We have now two classes. The first class, which is defined as it contains most of the red points, and second class, which contains most of the blue points. So if you look at this blue class, the Gini index here, so if you look here, the Gini index is 0.5, right? So this is the maximal error. Like this is the maximal error that it would have. So we need to minimize this Gini index, right? So after this is split, then you find that the Gini index has already reduced. So now it's 0.3. And the number of the samples altogether in the blue class is 108. And those 108, they are 22 red points, those, and 86 blue points. And this class is classified as most likely blue class. On the other hand, the red one, the Gini index is also reduced. So the most important thing is that we need after each split, we reduce the Gini index. Gini index is the error function or the loss function that we use. So after this is split, the Gini index now is 0.258, and this class here, it contains 92 sample, which classified as 78 red points and 14 red points. And from here, if you look at the train accuracy, the train accuracy is around 82%, while the test accuracy is 79%. So it's still low, we need more. So as we need more, then we should have do more splitting. Split once more. So we take this branch and we split it twice. So now if we split not the y but the x, right? So if you split now the x to be less than 0.5, like this one, this one here, negative 0.5, like here, you should have two classes. So both classes actually have Gini index less than the one before. If you look at this one, so we reduce the Gini index again. So in this class, it has a Gini index of 0.16, and it has 11 samples. This class here. So the 11 samples here, they are classified as 10 red points and only 1 blue points. This one, and that one is mostly red. But also still, if you split the other one, you still have the Gini index of 0. This class here, or this node here. So in here, we have 5 samples, 5 points. All of them are blue and no red points. So here, we hit a leaf. So we keep that one. We are not splitting this anymore because the Gini index is 0. So we hit the global minimum of the loss function. So we keep that one. We do not split that one anymore. But we have to split this node, and that one. And now if you look at now the train and test accuracy, so now the train accuracy is 89.4%, while the test accuracy is 88.5%. Look at the one before, then we have an increasing of the classification accuracy. Yes, please.
How were we deciding the decision to split?
The model, the decision tree tried to solve. So it tried the best classification. So I try, okay, if I split here, and maybe I get the Gini index of that, but if I try to split here, then I have a Gini index of that, so I try all it does all the trials. Okay. Until it finds the best minimization or the best value for the minimum of the Gini index. Okay, good. But now the train accuracy of 89% is not that good. We need to split more. We need more accuracy, so we split more. So another split here. So you see, you increase the number of the leaves that you have. And here we have actually 2 pure classes here, like this one, that one, there, and this is the one that we leave at the beginning, right? So if you look at that one, we have this one, right? So we don't split this anymore. Here. We just split other. Yeah, please. Please, a bit loud. He just asked this question. Okay, so we do not choose the y. The model the decision tree actually tries all possible trials and all possible values for y, such that the Gini index is minimum. So we don't do that. And now, as you can see, now the model tries to take the first feature, the second feature, and try every time find the cut on the threshold on y and x, such that the splitting is going to minimize the Gini index. And now the question is, now we have a 2-dimension data. So what if we have 3-dimension, 4-dimension, 5-dimension, high dimension? What do you think now the splitting here would be, right? Like instead of having data on x and y, I have data on x1, x2, and 3, right? So the model tried first to find the threshold value on the x1, and then try the second one to try another feature, x2. The third one, on the third splitting, it try x3, and etc. etc. So it takes or utilize all the information from all the dimensions of the data points, such that it can find or it finds the best classification between the data. Okay, good. So now we have a train accuracy of 94% and test accuracy of 91. Do more splitting here. Then we have an increasing accuracy. So we have a train accuracy of 96.8 and test accuracy of 92.5. And please keep in mind, the leaf that we have, we keep it here, right? We don't split it. Well, so do more splitting. Oh, look. I noticed that one, right? That's the overthing. Yes, please. So that is the overfitting here. Any intuition why the accuracy is decreased here from this plot? Can you find the source of this degradation or index of accuracy? Yes, please.
I'm trying too hard to fit to my exact model. Not when I introduce anything that's not.
Yes, yes, but can you find the source, the point that makes the problem here? That's true. That's true. So now the model actually creates like one node, right? Complete node or complete leaf that to classify only one point. But as you can see, it's only one blue point in the middle of a bunch of red points. So most likely this point is red points, or it comes from a noise, you know. So it should not be there. It should be here, right? But due to some noise, when I do measurements, I measure it with some error. So this point shifted from here to there. So the model actually creates a new class or a new road for these points. Also here, same. You see? So this is the source and this is the meaning of the overfitting. And I hopefully now it's clear. More, then you see? The train accuracy actually increasing, keep increasing. But the test accuracy is going down. Okay, so any question in the overfitting? Okay. Okay, so now the question is, how can we control the overfitting in the decision tree? And here I want to ask the question, like in the polynomial model, when we have this, when we try to find nonlinear regression model, like in the last lecture, right? And to fit some nonlinear data, and then we said, okay, and instead of the linear regression model, we could have a polynomial model with lots of degrees of freedom. But this model actually overfits when we extrapolate the polynomial to high level or high degrees. So does anybody remember how we rectify the overfitting and the polynomial models? Yes, please.
We added a penalty term.
Yes. So we regularize the model, the polynomial model, but adding a penalty term that penalizes the model if it has more degrees of freedom, right? So exactly the same here. But here, we don't have like the degrees of polynomial, right? But what we have the large leaves. Exactly. Good. So the first one is that to control that, we can prune the statistically insignificant leaves by letting the tree actually classify all data, all the points, until it has like accuracy 100% or something. And then we trace back the leaves and the tree, and then we can prune the tree from the branch or the leaf that has a large statistical error. The second one is that we can consider the depth actually of the tree as a hyperparameter. Like I said, okay, I need a 25 split, I need 30 split, and after the tree does this 25 or 30 splitting, then I measure the accuracy. Then I try to increase more and measure the accuracy. Increase the splitting and measure the accuracy. And at the point that I found the test accuracy is decreasing, I said, okay, that is the best depth of the tree that avoid the overfitting problem. And actually, this one is the one that we use when we deal with the machine learning models. Okay, so as you can see from this discussion, that a decision tree can always get 100% accuracy in the training, but there are two main problems. The first one is that we need infinite time for large data sets, right? So we need to classify if we have, like for example, this data set for the ImageNet, or if you have billions of data, like a Facebook, for example, Facebook data or Google data, then you may end up with forever try to analyze the data using this one. And also, overfitting for uncertain data, it's very easy to overfit, as you can see. So we need a solution to solve these two problems. What the solution is? Ensemble learning, right? So we can combine different decision trees to solve these two problems. The first one is the boosted decision trees. The second one is what's called random forest. Well, so this is a single tree, and the boosted decision tree is that we like take a random tree from the data, just random tree, and then we can find the best classifier on that one. Like we can find the threshold that can best separate between the two classes. And now try another another classifier according to the based on the first one, and try to boost the classification boundary sequentially. So we train the tree after tree after tree sequentially. I'm going to show that in a moment. On the other hand, random forest, from its name, we have the data, and then we do what's called bagging. So anybody heard before the word bagging? The other one is big.
Oh,
I'm talking about bagging. Okay, so bagging is a bootstrap plus aggregation. I'm going to discuss this. So what does that mean? We have the full data set, and then we take a random sample from this data set. But not only one random sample, but we take lots of random samples. And we train or we treat each of these subsample from the sample data as a separate tree. As far as we construct all the trees, then we can sum over all of them. So this is what's called aggregation. Aggregation means average over the list. Well, so how that works? Okay, so boosting, the name of boosting, the meaning of boosting, that it is a method for combining many weak learners or trees into a strong classifier or a strong learner. Okay. So for example, consider this kind of data that has x1, x2, and then we have an x and o's, different classes. So for the first, like the initial split, one can find this dashed red line here to classify between the data, right? But actually, if you do that, then you can find that those are O's, and here there are X's, but still some misclassified points inside the second class, right? So what can we do? We just like label this data, and then we increase the weights of this data. Those misclassifieds, we increase the weights. So what does that mean by increasing the weights? So as far as you increase the weights, that means you tell the loss function that it has more error, right? So the loss function tries to minimize the error by minimizing the weights of those points, of those misclassified points. That means I have like I'm telling the decision tree, please focus on those misclassified points here, and then it updates. So it tries to shift the previous classifier or the classification boundary a bit to the right, right? So for the boosted decision trees, we boosted the purity in the tree nodes sequentially. So we start with the data points, and then we can actually classify or identify the misclassified points. How can you know this? Because this is a training session. So this is supervised training method. So we know about this, right? So when you train, you attend the last lecture, right? So you know the difference between supervised and unsupervised, right? So this is supervised version. So we know actually. But after we train, then we test. Give some new, unknown, unseen data points. That's the measure. And then we give a large weights, and then try to update the classifier. Then we define or identify the second misclassified set of points, and then we update the classifier, and so on and so forth. And then the simple boosting method is that we sum, right? So we sum those classification boundaries such that the last learner that we have, or the last classification boundary, is very small. Look at here. So we have this one, we have this one, we have that one, and if we sum of all of them, we have this one. Right? So this is a boosting method. Of course, there are lots of ways to advance the technique on the boost, like add a boost, add a grad, and all of these kind of things, where we're going to discuss it tomorrow. But this is just like a naive sum of the weak learners or weak classifiers to have a strong one. Well, and now what about random forest? Random forest work in a bit different manner, but also kind of in sample learning. So we randomly do some bootstrapping. So does anyone know what is a bootstrap? Bootstrap? Yes? No, not this one. It's not this one. No. It's a statistic. This is in statistics. Yes, please? A bit close. Any try? Huh? Okay. So bootstrapping is random sampling with replacement. So we have a very big data. We sample from this data randomly, and this is one sample. We sample again from this data, but the sample that I've already taken, I put it back, right? And then sample again, and sample again. So this is the bootstrap. So it's random sampling with replacement. So in each of the subsamples that I got from the main population, right, there may be like a repetition. Like I have here, this is the main population, right? So I have lots of points here. Then I want to sample sub samples, small samples from this one. So I capture this one for the first one, and maybe I capture those two from the second one, maybe I capture those from the third one, and so on and so forth. Right? So this is the bootstrapping. Aggregation is just average of all the bootstrap samples.
هو العينات السامبلز ممكن يحصل ما بينها تقاطع
This is what I say. This is the replacement. So you randomly sample with replacement. So the points here can be in this sample, and in this sample, and in this sample. Right? Yes, please.
Does the bootstrapping like perform exclusion of extreme data? Exclusion? Like what excludes the extreme data? Like when
it helps. It helps. So if you so we have two problems here that we want to solve here, right? If you use a decision tree, single decision tree, right? So one of them is that try to reduce the time for very large data. So this is one thing to speed up the calculations, right? Any question? Okay, good. So first we just have this very big data like this one here, and then we bootstrap from the data, and then each one of those is considered as a separate tree, completely separate tree. This tree does not talk to the second one or the third one or its neighbors. So they are completely separable trees. And once those trees are found at this classification boundaries, we just average over all the trees. And those two are called bagging. Okay. Well, so example. So we have a tree 0, tree 1, tree 2, tree 3, tree 4, and at the end we find the random forest. Right? So we take all the classification and average all, so we have at the end a very a good classification or classification boundary. Okay, so this picture actually I took it from this website. It's not mine, but it's a very nice picture to show you. Give you a concrete and visual comparison between the decision tree, single decision tree, and the random forest and the AdaBoost. AdaBoost is advanced technique from the boosting. So this is also, you can call it the boosted decision trees. So given those points here, then you can find that the decision tree actually can reach an accuracy of 75%. Those are the test accuracy. While the random forest actually can reach an 82%, and the boosted decision tree can have an 85. For a different set of points here, then also the decision tree has 82, the random forest 85, and the decision tree or boosted decision tree an 85. Also here, the decision tree is the lowest, and the boosted decision tree is the best. So actually, both of them can solve the problems of the large data sets and the overfitting. But let me show you a comparison when one can use the boosted decision tree over the random forest. So first, the high classification accuracy, as we saw here, that always the boosted decision tree can reach high classification accuracy over the random forest or the decision tree. The statistical instability, that the boosted decision tree has a problem with the statistical stability and overfitting problem because we boost the tree sequentially. So if there is a misclassification, or sorry, if there is a noise, then this counts actually. So it's very easy, can be easily hit an overfitting problem. But for the random forest, this problem is no longer exists because you average over all the classification. So if have different boundaries, different classification boundaries from this separated or the parallel trees, and then you average over all of them. And of course, averaging, it can somehow mild the dependence on the statistical insignificant point. So this is exactly the same, easy overfitting. Yes, the decision tree, boosted decision tree can be easily overfit, while random forest is a bit stable against the overfitting problem. And the last one is that the time consuming, the boosted decision tree, of course it's time consuming because we sequentially boosted the tree, while random forest is not, because we do things in parallel. Okay? So, okay, so now it's 4, so I'm going to end here. We still have to write. Thank you. So we have just like how to see how to evaluate the model, and this is we are going to get to discuss tomorrow together with the deep learning models. Any questions so far regarding this one? No? Okay, good.
هروح بقى دكتور الحق البوس. استنى كده خلاص. ها؟ ربنا يكرمك.